Let's go through a sequence of reductions for this circuit and identify all currents and all voltages. If I hover my mouse over this battery, I can see that its voltage is 50 volts. The first thing I'm going to do is find the circuit current, which means I'm going to reduce all of these resistors into a single equivalent resistance. This 3 ohm and 5 ohm resistor are in series, so I can collapse them pretty easily. A 3 ohm and 5 ohm resistor in series can be replaced by an equivalent 8 ohm resistor. This is what that looks like. Everything's the same. I just replaced 2 resistors in series with an equivalent resistance. Now I can see I have 2 8 ohm resistors in parallel. Here's my expression for resistors in parallel. So I'm going to replace these 2 8 ohm resistors in parallel with an equivalent resistor that's equal to 4 ohms. So this is what I have now. Obviously that 6 ohm resistor and 4 ohm resistor are in series, so I'm going to combine them. And this is what I have now. That 6 ohm resistor and the 4 ohm resistor in series collapse into an equivalent resistance of 10 ohms. You can see I have a 4 ohm resistor in parallel with a 10 ohm resistor. So here's how I combine them into a single equivalent resistance. And here's what I get. This precise number of 2.857142857 is approximated by Falstad as 2.9. However, it does store the precise value, as you can see here. Finally, you can see I have a 2 ohm resistor in series with that 2.9 ohm resistor. I'm going to collapse them into a single equivalent resistance, and that's it. You now see my circuit reduced to a voltage source and a single equivalent resistance. Ohm's law says that my circuit current, which is the current leaving my battery that feeds the circuit, should be equivalent to 10.294 amperes. If I hover my mouse over to any wire, Falstad indicates the circuit current is 10.294. And again, that's an approximation, but it does keep all of the digits. So in this case, my prediction is in agreement with the simulation. So now I'm actually going to work backwards. I need to know the voltage drop across that 2 ohm resistor. I know the current going through it. I already figured that out. And I also need to know the current going through that 4 ohm resistor and the voltage drop across that 4 ohm resistor. This is a job for the loop rule. I have a voltage rise due to that battery, a voltage drop here due to that 2 ohm resistor, and another voltage drop across that 4 ohm resistor. I use Ohm's law to find the voltage drop across that 2 ohm resistor, and from the loop rule I can see my voltage drop across that 4 ohm resistor should be 29.41 volts, and the current going through that resistor should be about 7.353 amperes. If I hover my mouse over this 4 ohm resistor, I can see the voltage drop is 29.412 and the current is 7.353 amperes, so we have an agreement. So I need to move backwards again. I need to find the voltage drop and the current going through that 6 ohm resistor. I know the current coming into junction 1 is 10.294 amperes. I know the current coming out of junction 1 and going through resistor 4 is 7.353 amperes. So if I use the junction rule, I'm calculating that a current of 2.941 amperes should also be coming out of that junction and going through that 6 ohm resistor. Hover over that wire and Falstad is saying the current going through that resistor is 2.941, so that's an agreement. Here's Ohm's law to find the voltage drop across that 6 ohm resistor. I'm predicting a 17.647 voltage drop. Falstad is saying 17.647, so we're done with that. Stepping backwards again, I know the voltage drop across that 4 ohm resistor. I know the voltage drop across that 6 ohm resistor. I'll use the loop rule to find the voltage drop across that 8 ohm resistor. So marching clockwise, I remember I have a 29.412 voltage rise rise across this 4 ohm resistor, a 17.647 voltage drop across the 6 ohm resistor, and another voltage drop across my 8 ohm resistor. Make sure you remember the convention for labeling resistor terminals. That's the way you know if you're encountering a rise or a drop. The net result is there's an 11.765 voltage drop across this 8 ohm resistor. When I hover over this 8 ohm resistor in Fallstad, I get the same result. Ohm's law tells me that there should be a current of 1.471 amps flowing through this 8 ohm resistor, and Fallstad seems to agree. Junction rule says that I have 2.941 amperes going into this junction. I just determined that 1.471 amperes is flowing out of this junction. So junction rule tells me I should also have 1.471 amperes flowing out of this junction going to the right and through this 3 ohm resistor and that 5 ohm resistor. I can use Ohm's law to predict my voltage drop across that 3 ohm resistor. It shows 4.412, which according to Fallstad is correct. I don't need to use the loop rule anymore because I know I have a 5 ohm resistor and I know the current going through that 5 ohm resistor. So Ohm's law is predicting a 7.353 voltage drop across this 5 ohm resistor, and Fallstad says 7.353 as well. So that's it. We have determined all currents and all voltages for each resistor and each junction in this circuit.